So you are doing this for machine learning, right? For data science,
Yes,
machine
ma'am.
learning? Yes.
Yeah.
So we learn according to that. Norm of a vector we'll have four types. Okay, first L1 norm, and another name of this norm is Manhattan.
Oh, okay. I think I've done this in machine learning, ma'am.
Yes. Do you remember?
Yes, I do.
Yeah. And next one, L2 norm, Euclidean norm.
Euclidean.
Yes. So shall we continue or shall we continue the next topic if you know
We can
them?
continue. No, no, we'll continue, ma'am. The same topic.
Okay. And third one is L infinite norm. And fourth one, we learn LP norm. So let us learn now one by one. Okay. A norm is a way to measure vector size. Okay. So we can understand as like we have a vector. So as like we have this vector x and means passing through the origin. So what is its norm and what it mean? Like take distance from the origin till to here. So this length or you can say length of the vector is norm. Okay. So this distance or you can say this length is norm of the vector. Are you getting this point?
Yes, ma'am.
Okay. And norm of a vector denoted by this symbol. Okay.
Okay.
By using this symbol. Yeah. So now let us learn now types of norm. And let us and
Are
a
you
vector
writing?
can Can you see the whiteboard?
No, it's empty for me.
Okay, okay. I'm just resharing you on. Just a second. Can you see now?
It's empty still, ma'am.
Okay. Now, first of all, we need to learn the properties of a norm of a vector.
Okay. Okay.
Then we'll learn types. Properties of norm of a vector. First property, non-negativity.
Okay.
What it means it should be always positive, or you can say non-negative, because obviously it is a length, so we take always positive in value.
Hmm.
Are you getting this thing? So
Yes,
it should
ma'am.
be um, second property, definiteness. What it means norm can be only zero when vector is zero. Okay, norm is zero when only vector is zero. It is zero if and only if the vector is zero. Or we can say for zero vector, it is zero. Got it?
Yes, ma'am.
And next property, that is third one, is triangle inequality. So what is triangle inequality? The norm of a sum of two vectors, no more than sum of their norms. Like norm, I'll explain you why mathematically also. The norm of the sum of two vectors, sum of two vectors,
Is less than or equal to the sum of their norms.
yes, is not more than, yeah, I'll explain you mathematically also. Not more than sum of their norms. Or we can say this is, if we have two vectors x and y, then this must be follows. Okay, and we can express mm, graphically also. If we have two vectors like this, we have x and y vector, and vector addition.
Hmm.
Do you remember? So
Yes, ma'am.
Yeah. So it may be equal or less always norm of these two vectors. Okay.
Okay.
Or next property is homogeneity. What it means? Let us understand this. Homogeneity, what it means? When we multiply a vector by a scalar, then the norm of the vector by the absolute value of the scalar. Like if multiply, I'll explain you mathematically also. Multiply a vector by a scalar, then the norm of the vector by the absolute value of the scalar. And we can understand like mathematically as we are multiplying a vector by a lambda, which is a scalar. So when we find its norm, then we can represent it as just multiply the norm by absolute value of lambda. Got it? And where lambda is scalar, which belongs to set of real numbers. Got it?
Yes, ma'am. Is there any other property called degenerateness or something, ma'am?
I'm not getting you. Just can you repeat it, please?
No, degeneracy or something. Is that only non-negativity?
Yeah, I'm now using the headphone. Can you repeat, please? Non-negativity
Is there
first.
an
First, yeah.
is there any other property called
No,
degeneracy or something?
no.
No.
Here we don't have in mass. Okay,
Okay.
maybe you have in like data science. Okay, so we if you need that, then I can explain you. Otherwise, in mass, these properties are enough.
Okay.
Okay, yeah. So how can now let us learn the types of norms. L1 norm or Manhattan norm. Okay, and first of all, even you know because you are doing that data science master, so obviously you know that I'm just asking you uh, like x vector having this component can be expressed as, you know this very well.
X1, it'll move X1 and the X1 units on the horizontal axis and X2 units on the vertical
Yes,
axis.
yes, exactly, you know this, right?
Yes. Yes,
So
ma'am.
let us move the next. L1 norm. Now let us learn L1 norm or Manhattan norm. So L1 norm is denoted by this symbol using 1 here in suffix. And this is equal to absolute value of x1 plus absolute value of x2. Got it?
Yes, ma'am.
Yeah. Or we can represent mathematical notation means having more than these two, then we can how can we express this albanome by using the symbol summation I is equal to 1 to up to n, an absolute value of xi. You got it?
Yes, ma'am.
Yeah. For n values, we can find as by adding all of these. Next, let us learn about L2 now, or Euclidean norm.
This is normal distance formula, right, ma'am?
Yes, yes. So if you know all of them, then we can move on next topic. Shall I, or you want to revise all of these?
So if it would be x2 square plus x1 square under root.
Yes, exactly.
Okay. So
And
general
we can
form will be,
use, yes, general form we can express as square root of, just a second, summation I is equal to 1 to up to n, and we are taking here absolute, square of absolute value. Got it?
okay.
Now, let us learn L infinity or max norm.
Okay.
Okay, and which is equal to the absolute value of the largest component. Okay,
Okay.
yeah. L infinity or max norm. So it is the absolute value of the largest component. Like if x2 is greater than x1, then uh, max norm
L.
can be defined as absolute value of x2.
Okay.
Okay, or we can express in this standard form by using the symbol. Means we can take max value out of ith value, and obviously we take absolute value here. You know why? Because we take a norm always positive. That is why here we are taking absolute value of them. Are you getting this point?
Yes, ma'am. We take
Yes.
absolute value as we want to maintain that non-negativity property.
Yes, exactly. Now let us learn about LP norm. means this is the generalized of noun. Like we put here, p is equal to just 1, 2, and infinity. Okay, in
Okay.
this form, and we can find any one of these norms. Okay,
Okay.
this is about only them, which we have found already.
Hmm.
Okay, yeah, nothing else, nothing different thing. Okay, so if we put, so what happened when we usually put 1 to an infinity to find L1 norm, L2 norm, and infinity. And now we are finding for 0 when p is equal to 0. Okay.
Okay.
So when you put p is equal to 0, then we'll find L0 norm and can be expressed as,
1 minute, ma'am.
yes.
Yes, ma'am. Please continue.
Okay. So this can be, 0 norm can be find as number of non-zero entries in X. How can we find it as? Like we have X is equal to 250. Okay. So here we can find 0 norm. As we have non-zero, we have two entries only. So norm is 2. 0 norm is 2. Okay.
Yes.
Number of non-zero entry. You got it?
Yes, ma'am.
So this is about norm till here. Now shall we start the next topic or want to ask anything?
Uh, what if P is 3?
Just a second. Actually, we usually find a norm for only 1, 2 and infinity. Okay?
Okay.
Yeah. Not for many values. So formula is defined for only 1, 2 and like infinity. And particular cases means in rare cases we use this 0 norm also by observing this vector. Okay?
Okay, ma'am.
Yeah.
A norm is basically a way to measure
Length,
vector size.
yes, vector length you can say. Vector size. Or simply you can say length of the vector, okay?
Okay.
Yeah. Now you got it? Or shall I
Yes, ma'am.
repeat anything? Okay,
No,
okay.
ma'am. Now
So
we'll do
now
enough.
let us, yes.
Okay.
Okay, so first of all, let us learn inner product. Then we learn inner product space. Okay?
Okay.
Uh, so do you remember dot and cross product of vectors? Do you remember that?
Dot product I remember is like scalar multiplication, but cross I don't remember.
Okay, it's okay. So I'm telling you here dot products of vectors. Okay.
Okay.
So you remember that or
Can we revise
shall I?
it?
Sure. Okay. So how can we multiply two vectors by using dot product? Let us have 2, 3, and 5 we have, and just find the dot product with 7, 1, 4. So to find dot product, just multiply corresponding element, just 2 with 7 plus 3 with 1 plus 5 into 4. Got it? Like this, I'm telling you.
Okay.
Like 2 dot 7 plus 3 dot 1 plus 5 dot 4. So obviously we'll get 14 plus 3 plus 20. Okay. So 37 we have. Okay. You got
Okay.
it? Yeah,
Yes,
this is
ma'am.
the yeah dot product. So now let us learn our no, next topic.
What is cross product, ma'am?
Cross product will always like we find the determinant like if we have vectors like uh, just put here I j k unit vectors, and if you have
Mm-hmm.
these two vectors to find, so we'll write here. Okay, it's 2, 3, 5, and 7, 1, 4. Then we'll multiply. Then just to expand this determinant. Okay, are you getting
Uh,
this?
so for I, it will be 3 into 4 minus 1
Yes,
into 5.
yes, yes, exactly. Yeah.
Okay.
Okay. Yeah. So in this way, we can find the cross product. You want to do this in detail, or is it enough for you? What do you say?
It's not needed for inner product, right, ma'am?
Yeah.
Then we can go ahead.
Okay. Okay. Tell me one more thing is that, like, do you have your own material, or shall I use my own for all the topics?
1 minute, ma'am. Could you repeat?
I'm saying that, do you have your own material which you got from your university, or shall I use my own for all?
Every week they give me some material. Do you want me to share that,
Okay.
ma'am?
Okay, you can share me if you want. If you have right now, then you can share me.
Yeah, I can. Just give me 2 minutes. But for
Sure.
now, we can continue using
Sure,
your
sure.
material.
Sure, sure. Actually, I'm asking about because different books sometimes use different symbols. That is why I'm asking.
Okay. The inner product will come under week one's topics, linear algebra.
Okay.
Is it? I'm asking, ma'am.
Okay. So let us start the topic inner product. an inner product on a real vector space V is a function that associates, I'll explain you each and everything, or real number u comma v with each pair. I'll explain you each and everything. I'm just writing with each pair vectors in V in a such way that the following axioms are satisfied. Okay. So what are means an inner product is a function, okay, on a real vector space V, and we'll choose this number like and in a such way that they are satisfying the following axioms. Okay.
Is a function on vector space V.
Yes. Okay.
Okay.
Yeah, and it must be follow the these axioms. First, this u comma v is equal to this v comma u.
What's this called, ma'am? Symmetry.
Yes, exactly, symmetry axiom. Okay, or we can mention over here also. I'm just mentioning here. First, symmetry axiom. Have you sent me your material?
Okay, I'm sending it now,
Okay,
ma'am.
just send me. Okay, it's okay. You can send me later.
Okay.
I'm just checking your symbols. Okay, that is why I'm asking. Next, additivity. Okay, next axiom is like this. And here, u, v, these vectors belongs to vector space. U, v, w belongs to v. And we'll choose here alpha belongs to f. Scalar. Okay.
Hmm.
So u plus v comma w can be expressed as u comma w plus v comma w. Got it?
Okay.
And next is homogeneity axiom. And like this, alpha into u, comma v can be expressed as alpha into u, comma v.
Ma'am, I can't see that. Can you scroll up?
Sure. Now can you see now? Or shall I write on next page? Okay, I'm just writing on next page.
Okay.
Next axiom. Homogeneity means if we multiply a scalar like this, alpha into u, comma v, can be written as using this axiom. Okay. And next property, the next axiom, or you can say next property is this v comma v is greater than or equal to 0, and this v comma v is equal to 0 if and only if v is equal to 0.
And this is
And
called?
this is positivity axiom.
Okay.
Okay,
Okay.
this is positivity axiom. And now we can these are the axioms for inner product. And
Hmm.
now let us learn the inner product space. Shall we?
Okay. Yes, ma'am.
Okay. You got it, or shall I explain you anything if you want?
Uh, I understand it, but I just want to know if there are any examples or something.
Sure, sure, we'll do further. Okay? We'll do surely. Just a second. I'm just giving you some examples. For example, if u is equal to vector 1 minus 1 2 and v is equal to 2 0 and 1, then this inner product of u and v can be expressed as in this form. Write this vector, this 2 0 1 as in this form. Just multiply with this if we are taking in matrix form, okay, or otherwise you can multiply in by using this form also, okay, you can
Okay.
multiply in this form also. If you are using matrix form, then you need to write one is in row form and another one is column form,
Column form.
okay,
Okay.
or just simply multiply this way you can represent this inner product.
1 minute, ma'am.
Yeah. Hello.
Yes, ma'am.
Yeah. So we can find this inner product as you can find by using a matrix property, or you can just multiply by using dot product. Okay, same
Okay.
as. So you got it now?
Okay. Yes, ma'am.
Yeah. So obviously, you can just multiply by changing order. Also, result will be the same. So it is satisfy the symmetry axiom. Okay.
Yeah.
Yeah. Similarly, we can do for this additive axiom also.
Okay, ma'am. I'll take it as homework to prove them.
Sure, sure, you can.
Okay.
Okay, you can do this. And similarly, you can prove for this homogeneity for these giving vectors. You can prove it. Okay.
How to prove positivity?
Positivity means this product will always greater than 0 or
Okay.
equal to 0, and 0 only when we have both vectors is
As
equal to 0
zero.
means, yeah, if we have the same vector, okay, we are multiplying it to itself.
Hmm.
Okay, we are talking about here, we are multiplying a vector to itself, then product of this always greater than or equal to 0, not be negative. Okay.
Okay.
Yeah.
So a non-zero vector, when you find its inner product, it will always be greater than zero, and if it's zero, it means that it's a zero vector.
Yes, exactly. Now got it.
Yes, ma'am.
And now you can prove it, like with take any one of vector of them, then you can find this condition. Okay, just multiply it to itself, then you will always also get the same result, like either greater than, because obviously greater than 0, because this is non-zero vector.
Hmm.
Okay, shall we do the next topic, or do you want to ask anything?
Ma'am, before that, is it possible for you to share the screen and like show me the assignment and for us to like break down what topics are under each so that when we cover it, I'll know.
Your assignment
Yeah.
right now, because
Would
I'm
it
using pardon.
it won't be possible to share screen with that?
Yeah, because I have one phone, because I'm using another device right now. That's why.
Oh, okay.
Okay, we still need some more topics to do the assignments. Okay,
Okay.
I'm just checking that. Yeah.
2A is whatever you just taught me, no, ma'am?
Okay, I'm just checking. Not all, because we need to learn some more topics also.
Even 2A is just products. It's just properties of inner product.
Yeah, here we have to learn furnace inner product and also viewate mapping and here Hermitian transpose also we need to know them.
Okay.
Okay, not only inner product. Another topics also in here included. Okay, that
Okay.
is why. Yeah. So we'll do one by one and each and everything. Then obviously you will see that this assignment will be easy for you. Okay, after learning all of the topics.
But I'm
Shall we
just
do the
scared
next?
that by 26th, we have to submit it.
Yeah. By 6,
Tw- 26th
26. Okay. On, I think on the Thursday or a Tuesday it is. On Thursday or
Thursday.
Tuesday.
Yes,
Okay,
Thursday.
okay.
Thursday.
Okay, either you'll learn all of these topics. In case you means if you'll not cover entire the topics, I'll solve for you, then explain these topics to you, then you can
O-
submit that. Okay?
Okay, ma'am.
Yeah.
Okay, ma'am.
So
Since we
in
have only
evening,
3 more minutes for today, can we do inner product space in the evening?
sh- sure, sure, you can.
Okay.
Okay. All right.
Okay.